This is a presentation with title Preservation Information Conceptual Model, and we'll discuss some knowledge management issues that are related to conceptual model for preservation. This is the outline of this presentation. At first we will describe the motivation and we will introduce the problem. Then we will identify some aspects of preservation. Later on we will focus on two issues, on the preservation of intelligibility and the preservation of provenance. Later on we will discuss about knowledge manager, which is one of the key components of CASPAR that handles these issues. Finally, we'll see the data that are currently available and the current deployments of the software component. At the end, there's a video demonstration of Gap Manager to make things clear. Some important questions are: what digital information preservation is? What kind and how much representation information do we need? And how this depends on the designated community? What kind of automation could we offer? So, we could say that the contribution of CASPAR is that we have formalized the notion of intelligibility and intelligibility gap that provides us some answers to these questions. But let's start from our physical world. This is the Vestos disk dated to 1700 before Christ. We still cannot understand it, so we failed to preserve its meaning. Or we still don't know how the pyramids were constructed, so we failed to preserve the process. The same problems occur in the digital world. For instance, how can we be sure that we will be able to understand this byte stream in future? Or how we will be able to understand how this image has been derived, with what sensors, with what kind of processing algorithms, and so on. So the question is, what should we preserve? Certainly we have to preserve the bits of digital objects. We should also try to preserve the information carried out by the digital object. This has many aspects: their accessibility, their integrity, their authenticity, their provenance, their intelligibility by human or artificial actors. Now we will focus on the notion of intelligibility. One of the key elements of OAIS is representation information. An information object needs a representation information to be understood. However, a representation information is an information object itself, which means that it also needs another representation information to be understood. So we need a way to stop this potentially long chain of representation information. So in order to abstract from the various domain-specific details, we have adopted a general module, a minimal one, that consists of two main concepts: the notion of module, where a module can be a software or hardware product, a schema, an ontology, and the notion of dependency, and we say that module T depends on T prime if T requires T prime in order to be understood, to be managed, and so on. So actually, we model the representation information of OAIS as dependencies between modules. We can formalize intelligibility based on this notion. For example, to understand the file readme.txt that contains English text, we need a text editor to open it and read it, but we also need the knowledge of English language. Or in case we have some multimedia performance data, this depends on the understandability of C3D motion files, the DirectX and MaxMSP modules. Or for example, astronomers use FITS files. To understand such a file, one has to understand the FITS standard, and so on. So, this pattern occurs in formally expressed knowledge as well. For instance, in the semantic web, one schema may extend or reuse several ontologies of other schemas. Also, in this case, we have a dependency graph over namespaces this time. So in this figure, namespace 4 depends on namespace 2, namespace 2 depends on namespace 1, and both namespace 1 and namespace 3 depend on the RDF standard. So, one arising question is how many dependencies we may have. Is there a limit to dependencies we need to capture? So, we need a systematic way in order to limit and cut these long lists of dependency chains. To do so, we introduce the notion of community knowledge, and recall that OAIS aims at preserving digital information for particular communities. So, we may formalize the knowledge that is already available to the members of that community by what we call designated community profile, where profile is just a set of modules that are assumed to be known to that community, which means that we don't need to analyze the dependencies of that modules because the member of that community already knows the modules. So here we have some modules that depend on each other, and there is one community, the community TU, that knows modules T3 and T6. Here are some auxiliary notions. The notion of closure, which is the set of all direct and indirect dependencies of one module. So here we can see the closure of module TX and the closure of module TY, which is also the closure of the profile TU. Now we can define the notion of intelligibility gap as the smallest set of extra modules that U needs in order to understand a module T. So here we can see that the gap between module TY and profile U is empty, since profile U already knows the dependencies of module TY, while the gap for module TX and profile U is the set of modules T1, T2, T4 and T5. So what does this mean? This means that if we want to preserve a digital object T for a community with profile U, we only need to get and store the gap of module T and profile U, because the rest is already known, and the other way around. If we want to deliver an object T to an actor with profile U, then the only extra modules we should deliver to him in order to return him something intelligible is the set gap between module T and profile U. This notion of intelligibility can be exploited in archiving, where we archive digital objects with some extra information. So, we exploit the notion of intelligibility to identify the extra modules we need to archive. And here we can see three different archival information packages of the same object O1 for three different communities. Here we can see a less symbolic example of modules, dependencies and designated community profiles. More specifically, we can see three digital objects: the object O1, which is a FITS file, the object O2, which is a PDF document, and the object O3, which is a zip file containing multimedia performance data. Moreover, we have defined three designated community profiles: the profile P1 in blue, which is used for astronomers, the profile P2 in red, which is used for casual users, and the profile P3 in green, which is used for multimedia users. And here we can see the gaps between objects and various profiles. Here is another example from the cultural testbed. This is an ASCII grid file, and below we can see the dependencies of that file. Now let's see how this theory has been implemented. We adopt semantic web languages for modeling modules and dependencies due to their advantages in terms of their extensibility and inheritance. So we have a minimal top-level ontology where a profile knows some modules that depends on each other. There is also a typology of modules that can be extended according to the needs. Another rising question is if there is a clear way for identifying which are the dependencies of an object. The answer is that the goal determines the dependencies. Take for instance the following example. We have a file 8.java. If we want just to compile it, its dependencies include a Java compiler, while on the other hand, if we just want to read or edit that file, then we just depend on the ASCII format. Or if we want to run a program, then we depend on Java Virtual Machine. So we can see that we have several dependency types that can be easily implemented using semantic web languages, since we just specialize the depends relation, and we extend the notion of intelligibility accordingly. So far we focused on intelligibility. We'll see more about the dependency management later on the demonstration. Let's now focus on another aspect of preservation, which is the preservation of provenance. So what we have done is that we have extended CIDOC-CRM ontology so that to be able to document digital objects. CIDOC-CRM is adequate for representing provenance information. Here we can see the architecture of models. At the top we can see CIDOC-CRM, and then we can have several domain-specific specializations of it. Metadata can be expressed as instantiations of the above schemas. Here we can see an example of the transfer of custody of one information object, like this painting of Van Gogh, and we can see the different owners of this object. In this example we can see how we can represent derivation history. More specifically, we can see that we have an image that was converted from JPEG format to PNG format, and another PNG image with a smaller resolution that was derived from the initial PNG image. Now we'll see an overview of the software for all these tasks. This is what we call Knowledge Manager in CASPAR. It comprises two layers: a semantic web knowledge middleware, which is the lower layer that provides a set of core services for semantic web data managing, like storing, querying, updating, and so on. And on top of this, there is another layer responsible for the dependency management and intelligibility gap, which we call Gap Manager. This is the whole thing. Here we can see the components of the CASPAR project, and in the red circle we can see where the knowledge